So this is mostly reporting the master thesis of the first two authors. That is under consideration at Patent Recognition Letters. So you can find the paper in archive, or you can also go to our GitHub. If you put Halmstad University Biometrics, there you can get also the paper and the database that has been used, which is also made publicly available. Just skip. So the motivation of this work is that beautification or AR filters are very popular in applications that use selfie images, like not just social media, but now in video conference applications, you also have filters where you can put artificial glasses, animal noses, and so on. So uploaded or restored images in different systems may be filtered or altered. These filters are readily available. They have low cost or no cost at all. They are embedded in applications used daily by many people and not necessarily to compromise face biometric systems. And indeed, it has been demonstrated that you use this type of filters, you get higher engagement or interaction in social media. So people are even encouraged to employ. But they can affect, of course, the capability of recognizing people or even detecting the face itself, because we are hiding, distorting, or concealing different facial parts. And this can be an issue in investigation, for example, where you have to automatically pre-analyze pictures or video, in many cases, given the amount of data that is unbearable to be handled manually. So here, we are, first of all, interested in quantifying the impact of this type of filters on face detection and recognition, because they can affect, both can be affected. And we also have implemented some strategies to try to counteract the effect of these filters. So one of the strategies has been to develop a method to reverse some of the applied manipulations. And we have also tested different training strategies by incorporating these filter images in the training set. So there are related works on these topics. So you can manipulate faces physically by makeup or surgery, or also in the digital domain, which is becoming quite popular, where you can achieve similar modifications that you could do physically, but you can also do other crazy manipulations like repositioning, resizing face landmark, and many different things, with the aim of improving attractiveness or pretending to look like somebody else, like a celebrity, or in general for fun, I would say. So we don't cover here, for example, presentation attack detection, where the purpose is that you try to impersonate or conceal your own identity. But of course, this could be used for that purpose, but we are just interested in the aspect of, okay, people is using this for fun, but let's see how it impacts biometric system. So some works are, existing works are concerned with detecting if an image has been retouched. And there are also works concerned with the impact of these manipulated images on performance, mostly using makeup or some digital surgery. So we have not found, well, I know that there are already such works in the literature, but when this thesis was done more than 1 year ago, there were not so many works evaluating the impact of these filters. So we have used 5 modifications using purely digital manipulation. So one manipulation, which is related to the images at the bottom, is, we call it Instagram filters. So we have taken the most popular Instagram filters used on selfie images just by analyzing the hashtags of the images, and the statistics saying these are the most popular filters that you have available on Instagram, where they mostly change contrast or light of the image. Then we have applied 4 more filters that we call AR, or augmented reality filters, where they mostly obfuscate parts of the face. So we have applied one dog nose, where you can see the picture. transparent glasses, and then 2 types of sunglasses with total opacity 100% or 95% opacity, where there is some information leak of the eye. So you cannot see here. But if we just plot the pixels of the image that has a value between 0 and 10, and we remap them to 0 to 255, it can be seen that the eye information is partially leaked in the picture. So it's still somehow available, and it will have impact in some of the results, as we will see later. So we have employed LFW database. So we have applied those filters to a portion of the database. Those users who has more than 10 images. And we have also employed Selfie database to train the image reconstruction method that I will explain here in the next slide. So we have applied to the images that contains sunglasses a UNet architecture, a modified version. So this UNet architecture has been proposed for image segmentation. So you present one image as input, and it produces a segmented version. We have retrained to provide an image with sunglasses and provide the original image, or try to reconstruct the image to look like the original. So this picture, so this network is just an encoding and decoding part. So this is why it's called UNet, with residual links. So the encoding and decoding paths are connected to try to concentrate on the parts of the image that change. And this network has been trained with the Selfie database, which is not seen in the rest of the experiment. So we also try to test generalization when this network is trained with one database and then is tested with a completely different database. You have here one example of the results when we reconstruct these glasses images with 95% opacity and with 100% opacity. So with 100% opacity, the reconstruction is not good at all. With 95% is somehow good in the sense that the eye region is rebuilt in comparison to the original image where we had the sunglasses. So at the end, we have 8 different data sets, 5 with the modification that I explained earlier. There are Instagram, dog nose glasses, and then sunglasses with 95 and 100. Then we have additionally the reconstructed versions of these 2 glasses databases, and of course we have the original. So we have in total 8 different data sets, which are the same images with different type of filters or reconstructions. So this database is available at GitHub, as I mentioned before. These are the names that we have employed in the paper, but they are not relevant here. And you have on the right side the number of images of each database. And you see that the numbers are different. There are percentages there that I will comment in a while. But what it means is that face detection is not having the same performance on each database. So I will explain this in a while. Before that, some algorithmic details. So the Instagram filter has been mimicked by open source neural networks. They are not available in Instagram. You cannot go to Instagram and apply to as many pictures as you want, so they are recreated. The AR filters are merged just on top of the image according to the landmarks, and face detection is done using the LEAP library, where we discard images where there is no face or more than one face. And this check is the explanation of why each database has a different number of pictures, because we apply automatic face detection and we just retain the images where there is a face detected. Our baseline feature extraction is a ResNet 34 system with input of 64 times 64. And we also employ a lighter network based on the SqueezeNet, which is ResNet 34 has 29 layers, SqueezeNet has just 18. And then we also apply a deeper network, ResNet, where you have 50 layers. So we have different feature extraction CNNs with different depths, different number of layers. We do biometric identification and verification, identification both in closed and open set, using distance measures and trained methods, and biometric verification just using distance measures. So let's go with the results. So these are the results of face detection. The table is upright, but I put quite small so you can concentrate on each different type of modification, which is the percentage or the success of face detection. So in the original database or with just the Instagram filters, the performance is 99%, so it's good. And the doc database, so if you just occlude the nose, you also get a very good face detection performance, close to 98%. But if there is some kind of eye occlusion, the ones that are marked in red, glasses and sunglasses, the performance of face detection goes to a 10% or even worse in comparison. In the reconstructed pictures that are glasses that we try to remove, we recover the face detection performance to a greater extent. So this reconstruction, at least from the detection point of view, it works good. But when there is eye occlusion, the detection performance decreases dramatically. And it's interesting that you get worse performance with transparent glasses. You would probably expect the opposite, and after examining in which type of images the detection fails, we realize that is people who already has glasses. So if we put a second pair of glasses, this seemed to hinder the face detection performance to a greater extent that if we just put black glasses on top of the eyes. So this was an interesting result that we observed that was in principle unexpected. Here we have the TSNA separation of the different users based on the different filters. So with the original Instagram and probably dog nose, you see that the separation of the different clusters is higher than when you apply glasses or sunglasses with different levels of opacity. So it gives the idea of how easy or in which type of database will be possible to separate identities better or worse. So these are the results of closed set identification with ResNet34 and distance measures. So we compared different distance measures and we got the best results with the Euclidean. So I will just concentrate on this distance. So with original database and Instagram filters, we get the best results, 90 to 93% identification accuracy. All the others, just occluding the nose or occluding the eyes with different type of glasses, then performance decreases dramatically, especially if we occlude the eyes. And after reconstruction, we get some improvement, but still we are not able to get the same performance than the original pictures where there is no eye occlusion at all. We have also trained some approaches to do closed set identification, and we have tested different training mechanisms. So for example, if you want to identify images with glasses, we have trained a system with the original pictures, so we just use that classifier, or we have tried a second option, a system which is trained with the same type of perturbation. To do so, you need to detect which perturbation is being applied to the image. And a third option is that we have trained a classifier where we put all the different modifications together. Of course, in the third option, you have much more training data. So we are not able, as we will see later, to attribute the improvement that we have observed to the fact that there is all possible modifications in the training data, or if we have much more training data here. So these are the results. So that two classifiers perform equal, at least if there is no sunglasses, and SBM does a little bit better with glasses. So I will just concentrate on the SBM, which is on the left part of the table. So if you train with the original images and then test with the modified images, this is the situation given the worst performance. So the average performance in that case, which is in the last row, is about 83%. If we compare the test image with the classifier that has been trained with the same time of modification, we get better results. The average is 91.3. But if we train the classifier with all the modifications together, this is the situation where we get the best results. And indeed, with the majority of modifications, we are 94% or above, except one case, that is reconstructed images with total opacity. But still the results are 82%. So just with training a classifier and putting all the modified images together, we are able to obtain a relatively good accuracy regardless of the filter that has been applied. We have also performed cross-filter test. So rather than putting here a table, I've put colors. So black means 0% accuracy, white means 100% accuracy, and the squares that are in blue means that the classifier is trained with filters that do not include eye occlusion, and the red squares mean that the classifier is trained with images that involve eye occlusion and test with images that involve eye occlusion as well. So the brightest regions are inside these blue or red squares, meaning that if you train with pictures that has no eye occlusion and you test with no eye occlusion, you get good results, okay? If you train with pictures that have eye occlusion and you test with pictures that have eye occlusion, you also get relatively good results. And the regions which are outside the circles are the darkest ones, which means that you train eye occlusion, test with no eye occlusion, or the opposite. So depending on which part is occluded in the train and the test data, you get different results. And the darkest of all are this column here and this row here, which means that you train with dog pictures where you occlude the nose and test with glasses pictures where you occlude the eyes, or the opposite. And in this case, the intersection between the available parts in training and test data is leaving out the nose and the eyes completely. So you are just using, or the classifier can only use the parts which do not correspond to the eyes or the nose. And this is the case where you get the worst results. So this is somehow expected. We have also done open set identification with trained approaches. So these are the results. We have trained the classifier with 80% data of 100 individuals. And then we have tested with the remaining 20% plus 58 unseen individuals that were not used for training. And we just reported the SVM when it's trained with all the possible modifications. And this is because it was the best option in previous experiments. And here you have for the first time results with the 3 different networks that we have employed. In the paper, it's reported together and the results are commented later. But now that I put here the 3 networks, then you can see that the ResNet 34, which is the solid curve, is in the middle between ResNet 50, which is the deeper network, and SqueezeNet, which is a lighter one. And finally, we have the verification results only with distance measures. And again, here Euclidean seems to be a little bit better in the majority of cases. And again, if in the original pictures or just the pictures modified with Instagram filters, that they only modify illumination or contrast, you get an EER of around 2%. And the others were you have occlusion of the nose or the eye region, the results are worst. With dog nose, you have around 7%, and with transparent glasses, you get 8%. But when you put sunglasses, it goes to 12, 14%. After reconstruction, we are able to recover somehow, at least with this type of reconstructed image. We are able to go to 6%, which is still not the same as the original. So even if we somehow recover the eye region, this reconstruction still is not as good to provide the same performance as the original images. And finally, some comparison for the CNNs on closed set and verification. I commented previously open set. And here you have the same tendency that ResNet 50 is the best one. After that is ResNet 34, and after that is SquidNet. And ResNet 50 is showing so good results here that even in closed set identification, regardless of the filter applied, you get an accuracy of 97% or even higher. Remember that here we are trained with all the possible modifications in the training set. A good question would be, what about if we get a new modification? And that's something that I predict that some of you will ask. Also in verification, it's giving pretty good results, ER below 2.2% in most cases. Before, with ResNet 34, was here some cases where you get 12, 14% ER. And SquidNet, that is, this column here is doing relatively good in verification. I must say that I've not highlighted before, but ResNet 50 and SquidNet are two networks that we have trained in our lab on a much larger face database. So this could be a reason also why SquidNet, which is a very light network, is doing relatively good, at least in verification. So to conclude, we have studied the effect of filters that are typically found on social media, that on the accuracy of face detection and recognition. And some of them has been shown to be very detrimental, especially if they obfuscate the eyes. And to try to counteract their effect, we have implemented a method to try to reverse such manipulations, at least sunglasses. And we also evaluated the use of modified images in the training set. And overall, these strategies contribute to recover the accuracy to some extent. And depending also on the depth of the CNN employed on or the training set that you employ, you have seen that it also has influence in the results. And as future, we would like to improve this image recognition, for example, image reconstruction, for example, by adversarial training. And of course, there is also work to do on detect which manipulation is being applied or which regions are affected to improve face detection or face recognition further, like training algorithms based on the specific manipulation or just analyzing the regions that has been affected by the filter. So this is the end of my presentation. Thank you very much.